Good morning. My name is Junhe, a software engineer at Netflix. Today, we are going to talk about our workflow scheduler, a robust foundation for large-scale data pipelines. We will share our experiences and lessons we learned, including patterns we developed. Netflix is a data-driven company. Every decision at Netflix is driven by data insights, from the color used in the landing page to upcoming original contents. Data scientists, engineers, and even content producers all run their data pipelines to get the insights they need. Thus, the scalability and the stability of the data pipeline platform has become more important. Over the past years, we have developed a robust foundation to provide users a consistent way to manage and automate their data pipelines. This foundation is called the BTP Scheduler. BTP Scheduler provides workflow as a service to thousands of Netflix internal users. It is scalable and reliable, including multiple components, for example, Workflow Engine, UI, alerting, and abstraction layers such as DSL and templates. It satisfies all the needs of our users, including engineers and non-engineers. We will go over it in this talk. Here is the high-level architecture design. Our users use UI, CLI, clients to interact with the scheduler APIs over the gateway, which provides a public abstraction and hide the internal details. The gateway is also helpful while dealing with API instance. For example, we can shut down the gateway to disable the APIs, but still keep the workflow engine running. This greatly reduces the impact of the incidents. Workflow Engine is the core, which manages workflow versioning, the metadata, and the states of the workflow executions. It supports scheduling with trigger components, such as time-based cron trigger and event trigger. It runs user business logic in Docker containers over the execution engine. The core itself is loosely coupled with downstream services by sending state changes to an event stream. This foundation worked quite well to support a wide variety of use cases. Users use it to automate their normal ETL pipelines, train their machine learning models, and so on. Some services also use Scheduler to periodically run jobs. Here, we tried to abstract the common functions or reusable patterns from all use cases and add them to the scheduler in a loosely coupled way. We also found that human-readable DSL is very helpful and plays an important role to support heterogeneous use cases. At Netflix, users can write their workflow definition using DSLs in YAML, Java, or Python. YAML DSL is actually the most popular one due to its simplicity and easy to understand. Here is our current scale. The growth rate is quite high, you can see from this chart, and we observed about 300% increase per year. One best practice to operate a service with this scale is to build good monitoring and logging around it. For example, in the past year, we were able to find out that the scheduler would have scaling problems in the near future by those metrics. Then, we started the engineering work before it actually happens. Now the scaling problem starts to appear. The engineering work is close to complete. One lesson we learned is that in this scale, we may experience many unexpected problems. For example, we found that there is a large load spike at midnight every day. Thousands of workflows are scheduled to run exactly at midnight. We talked with those workflow owners, and many of them were okay to start execution at a different time. The reason they use midnight is just because they copied an example in our scheduler doc, which uses the midnight in its cron trigger. Then, the next lesson is that it is hard to ask thousands of users to change tens of thousands of their workflows, even if it is a tiny change. the communication and the correlation efforts will be much more than the efforts improving the system, which is the path we took to handle this peak traffic. Next, I will focus on the core component, Workflow Engine, and talk about its design and the technical decisions we made to better serve our users. First item is about whether to build a bare-bones engine or an engine including useful patterns. You will only support the core features. We could reduce the complexity and make the core well optimized. But it means we will push the work to the user side and ask users to repeatedly write the same logic or find a workaround. This might need thousands of ways to solve the same problem. It is much better to support users with common patterns than asking them to do it by themselves. I will use for each as an example. For each is a very popular pattern. Users use it repeatedly run the same jobs with different parameters, such as backfill data or parameter tuning. We might ask users to explicitly define each iterations in the definition, which is tedious and time-consuming for large iterations. Think about thousands or tens of thousands. Also, they need to create new workflows if the for each range changes. With the direct engine support, users just provide an array of parameter values for each and jobs to run. They can change parameter values without recreating the workflow. Similarly, we add supports of subworkflow and conditional branching. Subworkflow support allows a workflow job to run another workflow, and conditional branching allows run some jobs only if the condition is true. Directly supporting them in the engine enables us to optimize those features and provide a consistent way to realize those patterns. Additionally, DSL support can help to reduce the complexity to define it. Another related item is about static versus dynamic workflow. Static workflow is simple and easy to use, but it is quite limited. Oftentimes, users have to duplicate the same workflow many times just because there's very small changes. A completely dynamic workflow will be hard to manage and support. It is difficult to debug and or troubleshoot. Therefore, we developed and created something called parameterized workflows, which are initialized step by step at runtime based on current user-defined parameters. Users love it, and it is easy to manage and troubleshoot and also powerful enough for them to write workflows with rich functions. To further enhance it, we support two execution modes: runnable mode, which is not returning any data, and the callable mode, which returns output parameter values from the execution back to the engine. Here is an example of backfill workflow with 3 steps. In step 1, user computes the backfill ranges and returns the dates back to step 1. Next, for each step, uses the dates from step 1 to create for each jobs. Finally, in each of backfill jobs, it gets date from the for each and backfills the data based on it. As we just showed, parameters played an important role in our scheduler. We have to decide whether supporting dynamic parameters with code injection or not. Code injection is super useful and powerful, and our users love it. Together with other features, it makes the workflow very dynamic. But with the code injection, the security is a big concern. Also, users might write buggy code. For example, in the past, a user unintentionally wrote an infinite loop to create an array, which then eventually crashed the scheduler JVM. We could ask users to put the injected code inside their business logic, instead of in the workflow definition. But this will put a lot of work to the user side and also coupled the user business logic with the workflow. Eventually, we developed our own customized expression language to support code injection. During the abstract syntax tree parsing, we put the limits there to secure and protect the system. Here is an example to show how users write a piece of code in the workflow definition to validate the results. Next, I will talk about the execution control. What we found is that simple concurrency control on a single entity is not enough. We and our users want to control like how many workflows to run, how many jobs within one workflow to run, how many jobs across all workflows to run, and so on. This requires a multi-dimensional concurrency control. Also, users want a scheduler to automate data pipelines, but also have enough control of the execution order. We provide both low-level control and some predefined high-level run strategies. It turns out the predefined ones are good enough, and almost no one uses the low-level ones. It actually causes more confusions to the users, and later we remove those low-level ones. Here are predefined ones. Sequential is to ensure only one running in first in, first out order. Strict sequential is to handle the unexpected job failures. In this case, users usually want to pause the execution, but still include the new ones. For example, here, when the run 5 failed, run 6 to 12 will be included, but there is no new execution. After the underlying issue is fixed, the user then restarts the failed one to resume the execution. First only is to achieve idempotency. If there is an existing running one, the new one is skipped. Last only is to allow new run to cancel the current running one, and also parallel with the concurrency limit. It is also important to provide debuggability and the surface errors for users to troubleshoot. Both will improve the user experience and the worst time and efforts to implement. For debuggability, we support a breakpoint to allow users to pause the jobs in workflow. We also include error information, execution timeline, and milestones to artifacts to help users to troubleshoot failures. With all those learnings, will we always prefer adding more and more functions to the workflow engine? The answer is not always. In some cases, we move functions to other services or build dedicated services. This helps to separate the concerns and make the whole platform more scalable and robust. If any of those services is offline, the workflow engine can still run normally. Next, I will pass the talk to my colleague Harrington to talk about the other components.
Thank you, Jun. Hi, I'm Harrington Joseph. I'm a senior software engineer at the Big Data Orchestration team, and I work together with Jun building the next generation of scheduling tools. Let's talk about the DSL. The DSL stands for Domain Specific Language. This was the first component that we built that is user-facing in order for users to have a unique, simple, and unified way of defining workflows. For this, we picked YAML. We picked YAML because we wanted a static definition that anyone could use and read. So here's an example. The top section shows a trigger block that is completely optional, but it allows users to define how often they want their workflow to trigger automatically. In this case, it's defining a cron trigger that is saying that this workflow should run on a daily basis, and the time zone is US Pacific. So this means that this workflow is going to get activated at midnight in US Pacific time. You could use complex cron expressions or other time zones that are considered valid. Next, you have the workflow section. A workflow is defined initially by providing an ID, which is a unique identifier across the platform. Then you need to provide a list of jobs or units of work that your pipeline is going to execute. In this case, we have two jobs. The job one is a Spark job that all it's doing for presentation purposes is running a select one. Of course, you can do something much more complex than this, or provide a SQL file or a jar file. The job number two is a notebook job. And in this case, the notebook job allows you to execute Jupyter notebooks as part of your pipeline. All the user needs to do is to provide a URL or a path to the notebook so we can find that notebook on execution time. So this provides a common tool for users to define units of work, to define their workflows. From now on, all the workflows follow this structure, and it's fairly simple to understand what a workflow looks like and where the jobs are and what parameters it's using and so on. And it also complies with the following 3 principles. Readability. Anyone can read this. There's no reason to read buggy code or nested or recursive code in order to understand how the workflow should look like. All you need is a text editor and just read the YAML. Next, reproducibility. This is very reproducible because anyone can go find a YAML on any repo, copy it, maybe change the ID and push it, and you should get the same behavior. And then you can actually iterate over these, add new jobs, tweak some parameters. So it's very useful for users also to learn from each other. And debuggability. Because it's readable, reproducible, and it's also like people can actually iterate over this, then it's very easy to debug. Now let's talk about the CLI. The CLI is a command line interface that we built for users to interact with the scheduler. It is installable anywhere, meaning that users can actually install these on their laptop, servers, dev environment, Docker containers, you name it. And it's integrated with the platform. This means that it understands security. When a workflow is created, the workflow is shipped together with the user identity. So when the workflow is executed, it executes as the user, meaning that it has access to the same resources. It also provides asset management. If you need to ship, say, a jar or a SQL file, an encrypted file that you need to decrypt during the execution time, this tool also allows you to do that, and it takes care of that in a seamless manner. So here are some examples. The way that you access this tool is just by typing the scheduler command. Then you can create a workflow by just typing scheduler push and then providing the YAML file. From that point, you can run, activate, and deactivate the workflow by simply having the ID of the workflow, so you can just execute one of these commands. The last command, info, is actually very useful because it provides you ways to fetch information about a workflow, and all you need is the ID. So you can get information about like what the workflow status is, what the version, what the latest version is, what's the current active version, and even a link to go to the UI. So we also provide a dynamic DSL, and it looks like this. It's fairly similar to like the Airflow DSL. In this case, it's the Python one. As you can see, it's using the built-in pattern, and instead of operators, we provide what we call job types. But as you can see, this is exactly the same as the YAML definition. We also have a Java version, pretty much the same, just a little bit more verbose, but it's doing exactly the same thing. So you may be wondering, where did all the principles go? Well, if we look at the workflow creation, once you have the YAML gets pushed to the scheduler API by using the scheduler CLI. Now, the Python DSL and the Java DSL talk straight to the scheduler CLI, that is scheduler API. The scheduler API has the ability of computing a YAML for every new created workflow and then stores it on S3. This computed YAML becomes the source of truth for any given workflow. So at that point, if a user pings me and say, hey, I need help to diagnose my workflow and I understand what's happening, the workflow doesn't look how I want it or anything like that, I can just go and find that computed YAML and take a look, understand it, and then even iterate over that YAML without having to read that Python or Java code that might be a little bit trickier for me because I may not have the same libraries, I may not have the same dev environment, I may not understand what the user is trying to do in their code. So this is actually much better for us, and it actually complies with the principles that I mentioned. So it's readable, reproducible, and debuggable. Now let's talk about executions. Similarly to Airflow that provides operators, we provide what we call job types, as I mentioned. Our job types are built on top of different notebooks that we use as templates. And then on execution time, we basically just inject parameters that have been provided by the user into the templates for the template to actually use them during the execution. So we provide templates for like Presto jobs, Spark jobs, transport jobs, meaning that you can move data in and out, RDS, Elasticsearch, Hive, Iceberg, you name it, reporting tools, data auditing tools, notebooks, as I say, bring your own notebook, we'll run it as part of your pipeline, You can do the same thing with your custom scripts. You can bring a bash script or a Python script. We can also run it as part of your pipeline. And you can even bring your own Docker image and specify a custom entry point. So this is very good for our users because it provides a level of abstraction. Users that want to run, say, a Presto query, a Presto job, all they have to do is to provide the SQL statement that they want to execute. But they don't really need to know how the Presto job actually runs. They don't need to know the internals. They don't need to know which cluster we're talking to, for example. The next one is also standardization. All the Presto jobs and all the Spark jobs, all the transport jobs, they all run through the same templates. So therefore, if we find a bug, we can easily go apply the fix, and the fix is applied to every single job that we have in the platform. Our execution is done in a way that we run every single job in its own container. So this means that we get a clean and isolated environment for each particular run. And we default our runs to use the big data image. The big data image is a Docker image that has been built and carved by the big data infrastructure team, and it contains all the dependencies that we may need for any of the jobs that I mentioned before to run. And our default entry point is PaperMill. So PaperMill is a tool that allows you to run notebooks in a headless manner. This means that you don't really need the notebook's UI in order to run the notebook. So here's how it looks. We basically call PaperMill. We provide the path to the template that we want to execute, say the Spark template. And then what you see in pink is actually the output notebook, where we want these to be written. Like we want this execution to be written sort of like a log, but in a notebook format. And then we just have to provide the parameters that we want to inject into this notebook. So in this case, we're defining a parameter called Spark that has a key called script and a value of select1. So here on the right is the notebook output. As you can see at the top, there is this cell called parameters. At the bottom of that cell, you can see that there is a Spark equals a dictionary containing script equals select1. This is the parameter that we just injected when we made the PaperMill call. So this is very nice because users can actually see all the parameters that are getting injected into the notebook execution, so it's easier for them to understand what's happening. They can also see the rest of the execution that is actually the code that gets executed in order to execute, for example, in this case, the Spark job. So it's definitely readable. They can see everything here. Of course, we talk about abstraction, but this is a way of diving into details if you want to. It's also reproducible because anyone can download this notebook and run it locally. And it's debuggable because after you download the notebook and you run it locally, you can actually tweak the parameters and even tweak the internals of the notebook in order to achieve what you want. Then you can actually go back to your workflow definition and update your parameters accordingly. So on top of manual and time-based triggering, we also provide event-driven triggering. And it looks like this. If you look at the trigger section now, we have what we call signals. In this case, we have two groups of signals. So the first group of signals is defining two signals that says, I want to run this workflow when table A is updated and when table B has a partition updated. So we're able to do this because signals in the scheduler consist of the interpretation of events, and our platform is fully aware of events in the Netflix ecosystem. So we know when a table is updated, when a partition has landed, and so on. In addition, we also allow users to define custom signals. For example, I want to run this workflow when an application called My App has announced a signal called ABC. And this is also available for users because applications are able to emit events, and once these events get placed into our event stream, we can turn them into signals. So this is more efficient because there's no reason to waste resources checking if you're ready to run. It's also more accurate because you move away from executing when you think you have to. So instead of running hourly or daily or so on, you execute when you actually have to. This also applies for what we call job dependencies or input signals. So the workflow can actually be executing and until the point it gets to a job that has input signals. At that point, it needs to check if these signals have been satisfied. If the signals have not been satisfied, then the workflow is going to wait for the signals to satisfy in order to be able to run this job. So this is very similar to airflow sensors, with the main difference that this is 100% event-driven, so there's no pooling mechanism behind, there's no resource waste in this case. In the same way, we have output signals. Jobs can emit signals that can be consumed downstream either to trigger a workflow or to release a job that is waiting for a signal. And this is a very nice way to orchestrate jobs and workflows in a distributed manner. So in summary, I would like you to walk away from this talk understanding that for us, from definition to execution, our platform is composed from multiple layers. And all these layers have been defined with clear separation of concerns, and this has allowed us to provide a solid foundation to support multiple use cases and for applications to build on top of our platform as well. That's all I have. Thank you very much for your time, and I look forward to your questions.
Hello, and thanks for the presentation. We already have questions on the chat, but I'll start with a question of my own. Your strategy of using Jupyter notebooks as the pipeline source code is very clever, because you can do experimentation in Jupyter and then use the same code to actually execute the pipeline. But I was wondering, when you are in the experimentation phase, you probably want to do experimentation using samples of data or things like that. So I was wondering how you organize this. I mean, do you have samples done for every data set you can use later in production? How this works in practice?
I think I can take that one, and then I don't know if Jun, you want to add anything. Yes, that's a great question. It's something that everyone struggles with, because, I mean, replicating the same data center for tests and products is quite challenging. So we do have some test representation of some tables and data sets and stuff like that. Of course, it's not 100% like it doesn't represent absolutely everything 100%. But yeah, the users are able to fetch either some data from a real table, maybe they just gather a smaller set because it probably doesn't fit in memory or whatever they are trying to do. And then they can actually try to output whatever, like say that they're doing some ETL or something like that. They can output that to a test table so they can run over and over and over, or even they can output to a prod table, but that is under their own database. So it shouldn't actually be propagated or cause any impact on live table. However, the advantage of this is also that users are able to output to their own databases that are available in production for other people to consume as well. So you can see a lot of use cases where users have different way of inputting data to their tables, either like on the experimentation phase or in a production phase, and then they actually gather that on execution time or their workflow. Like machine learning is one of those examples where people are constantly tweaking their data and then picking it up live.
Yeah, one thing to add is that all the workflows is parameterized. So basically, from a source of truth or the actual production data from there, users actually can run all the whole or even multiple workflows, but by passing different parameters for the output path or the input path, and then just kind of run their tests without writing the data back to the production set.
Right, let's get some questions from the chat. I have several more questions, but let's start with the chat, and then if you have time, we can answer in the Hangouts. So let me just go to the beginning. I know you already answered some of them, but I'll repeat just in case someone is watching later and doesn't have access to the chat. So there's several questions that around how do you compare with Airflow and why using your own solution instead of Airflow, or other schedules. So can you elaborate a little bit about that?
Sure.
Go ahead.
Okay. Yeah, I go ahead first, and Harrington can add more. Yeah, we evaluated Airflow actually before we start this, and there's multiple things. First is definitely scale. In the Netflix scale, we have lots of use cases, and users does not always use Python. They may like use Java, or they may even don't know how to write code. Right? They just want to write some SQL to query some data. So first we provide like DSL, YAML, Python, Java, and users with all kind of backgrounds can use that. And also in terms of scale, we definitely don't want to because our data is in one data set. So we all the orgs actually here we don't handle, say, media team only use media data or something, so they can access all the data. So then we don't want to have like multiple schedulers clusters there. So when we take a look at the Airflow, it definitely cannot support this kind of scale. First is like a single workflow with thousands of jobs, right? This is the first kind of thing, and then also like tens of thousands of workflows, right? So Airflow cannot manage that in one single cluster, and our scheduler can. Also, I already mentioned the user experience, and then the last one is additional features that we provide, like cell code injection, event-driven, Harrington mentioned, and also those common patterns like for each workflow, all those things.
Yeah, I wanted to add two more things. One, when we started to work on this, I mean, it's been like around 4 years since we've been actually building this. And it actually predates that, like all these decisions. So Airflow wasn't quite mature around that time to the scale that we're talking about. So that was one of the decision factors. And then the other decision factor is, like, as every data platform is composed by tons and tons of services. But for the user experience, it's very hard to say, well, I have to run a workflow, I go to this service. I want to check my table, I go to the other service. So our philosophy in our platform is to provide a single and unified experience, like from the user perspective, it looks like a singular entity. And that was the other thing that we were looking at, like, well, how can we build a scheduler that we can integrate in the platform that feels like a single thing that is part of the platform and not like an extra piece of software. So that's why, like I mentioned, that we're able to react to events because we're fully aware of what's happening in the platform, and getting that with something external was actually fairly challenging.
There's another question. The workflow orchestration engine is a conductor. Can you explain what is conductor also?
The conductor is
yeah, they say the workflow orchestration engine is a conductor.
They're using conductor underneath or what?
No, well, the conductor, yeah, is a workflow, is a service orchestrator, which orchestrates microservices. We are not using in the current version of our BTP scheduler. We didn't use that engine. Instead, we use a code called Mason. And in the future version, yeah, we are considering a conductor due to its a horizontal scale.
Okay. They are asking if there's an example or how to available on GitHub. I don't know if it's open source, so I don't know if you have this.
No, right at the moment it's not open source. It's fairly challenging to open source the way it is because it's very integrated with Netflix. But we are exploring different options to see what we can give back to the community.
There's another question around YAML. I was expecting this. Don't you find define workflows via YAML limiting to complex advanced workflows as compared to define workflow via code? I know that later in the talk you actually showed how to do this via code, but if you want to elaborate a little bit more.
Yeah. So when we proposed YAML at the beginning, we had a lot of people brought that to us. Like, well, for me, it's much easier to be able to define things in code, or I just want to keep my code together, or like many different reasons. People wanted to dynamically generate very large workflows and stuff like that. So the initial idea was to just provide something very simple for everyone to use, and that's what the main reason of using YAML. And also, we wanted to be to have something that was readable. So YAML was the choice at that time. Then then we basically built the other two DSLs to support mainly applications, because applications do need to generate like their own workflows and stuff like that, and we wanted to provide them a way of doing this without having to generate a YAML and ship it. And as we did this, we basically just put this in front of users as well. So some users do actually use the Python or the Java DSL to generate the workflows. But as we said, like, we always compute a YAML at the end for us to be able to understand the workflow, because I don't want to have to set up a Java environment for it with the specific dependencies to understand what a user is trying to do.
There's another question. Do you have any plans to support or align with serverless workflow.io? It's an open source project as well.
Not familiar with it, so I cannot talk much about it.
Okay. Could you cover workflow DAG versioning?
Oh yeah, I saw that question. So yeah, we did not cover it during the presentation, but yeah, every time that, so when you create a workflow, you basically claim or restore that workflow ID. And next time you make modifications, you push new workflow definitions under that ID, they basically get appended to the same unit, but they get a version. And then you can basically switch between versions, either to rollback or to have two different implementations of the same workflow. June, I don't know if there is anything we can add there.
Yeah, so the scheduler managed versioning is a kind of linear way, yeah.
So we have to wrap up. We're running out of time, but I want just to remind everyone that you can continue this conversation on the Hangout room. You can find the link on the chat, and you can find also the link on the schedules page. So do you want to leave a last message? We have just 1 minute, so.
Yeah, I actually saw one very interesting question about events. So if you're willing to join us in the Hangout room, we can talk more about that. But yeah, thank you for joining us, and feel free to ping us either on social channels or anywhere you can find us if you have any more questions or you want to keep talking about this.
Yeah.
Excellent.
Thank you.
Let's go to the Hangout session then.